So today we are going to review vocabularies for the first couple chapters, and then we'll work some problems that will help you on the test. So if you go to page 10, you'll see the first summary. At the end of every chapter, there is a summary that talks about the vocabulary. So we'll go through all 6 of these ideas, and then when we start getting to chapter 5, we'll do some calculations and work on some stuff that'll help you for the test. So, number 1, statisticians use the method of comparison. They want to know the effect of a treatment or response, like getting polio. To find out, they compare the responses of a treatment group with a control group. What is a treatment group? The treatment gets whatever it is you're studying, right? They get punched in the face and the other people don't. If that's your study, that's a good study. Anyone want to sign up? So what's the control? The ones who don't get punched in the face, okay? And a treatment and control happens in something we call it's not an observation, it's an experiment. What's the difference between an observation and an experiment? Observing, you run around, you talk to a whole bunch of people, write down the information. And experiment, you get people and you treat some of them and you don't treat some of them. And there is a little bit of gray in between those two, but in general, an experiment is different than an observation. What can an observation tell you? What can an observation tell you, and what can an experiment tell you? What's the difference? So for observations, we use a word called, well, actually the book calls it association. Every statistics class I've ever taken calls it correlation. So in an observation, you can say A and B kind of happen together, or when A happens, B happens, or when A happens, B does not happen. But that doesn't mean that A causes B. It just means they're associated. And one of the really famous ones is bars and churches in New England in the early part of this country. As the number of churches increased, the number of bars increased at exactly the same rate and at exactly the same time. So you might say churches cause people to drink. But the other half of this is what? Population goes up, which means there are more churches and more bars. Okay, what do we call that third variable? I'm getting a little ahead of myself. What do we call that third variable? It's a something factor, confounding factor or confounding variable. Okay, well, I've gone into chapter 2, so let's keep going. Some of it's multiple choice, some of it's just free response. I don't really remember, but this first test really isn't that long, and I'll double check before I'm done and kind of let you know. Okay, what does it mean for an experiment to be randomized? Right. People do not get to choose if they're in the control group or the treatment group. What's wrong if people get to choose? We'll get to double blind in a second, but, well, that's true. You're right. I see what you're saying. If you know which group you're in, then it can't be double blind. It's not a true experiment because the people who say yes are probably categorically different than the people who say no. For instance, the wealthy people might say yes and the poor people might say no. And you want an equal, well, not equal amounts, but you want a representative sample of rich and poor and in the middle. And if people tend to choose, if they choose, they tend to put themselves in groups that are not heterogeneous. Okay, double blind. What does it mean to be double blind? The people issuing the treatment, like a nurse or a doctor, They don't know whether they're giving you the real pill or not. And that's one half of double blind. The other half is the person receiving the treatment doesn't know. And sometimes that's just not possible, right? Sometimes your experiment has to be single blind or even not blind at all. But ideally, we want a randomized, controlled, double blind experiment. And if we do everything right, then we can say A causes B. Okay, so go to the end of chapter 2. Summary starts on page 27. So we talked about observations. Okay. And so you'll see in the observational study, some of the subjects have the condition whose effects are being studied. This is the treatment group. The other subjects are the controls. So you might run around and you say, okay, we're going to do a smoking study. The people who smoke are the treatment group, and the people who don't smoke are the control group. Okay? But this is not randomized, it's not double blind, and it's not even an experiment. But it's unethical to do a true smoking experiment on humans. We do it to animals all the time. Here, mouse, we're going to fill your cage full of tobacco smoke, and you get to breathe it all day, and then we're going to see what happens to you. Okay, we do that to animals. I mean, right or wrong, that's what happens. But on humans, it it's just not ethical to say you have to smoke 10 packs a week, and then we're going to look at your lungs. So what's wrong with that? That's a good question. What's wrong with this? They chose their group, so are smokers categorically different than non-smokers? And the answer is yes, they are. Smokers tend to also do lots of other things that aren't safe, right? And people who don't smoke, they do lots of things that smokers don't do. And the point of an experiment is to make everything equal except the treatment. So if group A is absolutely identical to group B, but group B gets a treatment, then we can say the treatment did this. But when people put themselves in their own groups, there are so many variables, so many. Age, gender, right? None of those can be controlled for if people put themselves in their own group. Now, have smoking observations done us a lot of good medically? Yes. But you have to be careful when you do an observation because you're never totally sure that A causes B. There could be something else going on. For instance, the smokers might have a gene that makes them more likely to begin smoking. Okay? And that gene might also make them not live as long. But there's no way to tell because they chose smoking. So we want to do experiments as much as we can, but sometimes we simply can't. Okay, turn the page. We've talked about association. An observational study shows association. And the next one talks about confounding variables. So there might be something else at work here. Okay. So you see the little chart on number 4. There are two types of studies. Studies that have controls and studies that don't. Of the studies that have controls, you can either run one contemporaneous, which is like today, modern, or you can look at historical data. If you're doing a study right now, it can either be a controlled experiment or an observational study. And controlled experiments can be divided into randomized and not randomized. Randomized means people don't put themselves into their own group. Okay? So if I wanted to know the average height of girls at Emory High, okay, then, and I don't have enough time to talk to everybody, does it make sense to run and talk to the basketball team? No. Why? They chose to be there, right? So let's say I'm only allowed to talk to 25 girls. The basketball team is the wrong place to look because they put themselves in that group, right? And generally, that group is going to be taller than the rest of us, right? Most of them are taller than me. That's not hard to do. That's not a pat on the back. Okay, so do you see that, Ashlyn? That's why it's wrong. What would be a better way to talk to 25 girls? So if you only did 25 girls in the Spartan corner, did they put themselves there? Yeah. Okay. So we have to introduce this idea of random. Now, one of the funny things about people who run around and do surveys, and this is so crazy, sometimes they say, okay, we need you to talk to 50 men and 50 women. And they run around and they do these observations and they come back and they get this data and the data is way off. They're like, why? We talked to 50 random women, but if I get to choose, I might be intimidated by attractive people, so I don't talk to them, right? Or maybe short people make me really nervous, so I only talk to tall people, and that's a huge problem. So this idea of random has to truly be random. So what are some ways we could randomly pick 25 girls? Okay? So go just randomly walk around, but don't you get to choose where you're walking? It's hard. Okay, so let's assume everybody comes through the same doors to come in, and you decide beforehand, every 12th person, every 12th girl, I'll count. That's pretty random. An even better way, write down the names of everyone in the school, put them in a jar, swish them around, and pick out 25. Or you could look at the alphabetical list of all the girls and do every 12th one. And that's a little bit problematic because um, specific names might be tied to specific cultures. And so you might, all of the Z people are really tall because they're from Russia or something. I don't know. Okay. So it's really hard to do randomized, harder than you think. And you might say, I got up this morning and I just put on some random clothes. That's not true. You made choices, right? And your first choice, your choice of shirt, affected your choice of pants and shoes and the rest. But this shirt that I'm wearing was randomly chosen. No, because I have a random number generator at my house. It's called a dryer. Okay. And so my wife does the laundry, bless her heart, she's awesome. And she reaches in, pulls one of my shirts out of the dryer, sticks it on a hanger, and sticks it on the rack. That rack goes in, hangs in my closet, and I pick the shirt on the left. Uh-huh. And all the shirts that get washed get put on the right. So I wear all the shirts, then they all go get washed, and they get randomized in the dryer, and they get pulled out. So I didn't choose this shirt. It was the one on the left. Of course, that's not totally true because I chose a short sleeve. Oh, sometimes I do. Not very often, though. So when I wake up in the morning, I decide, is it a short sleeve day or a long sleeve day? So I wear short sleeves until about mid-November, and then I wear long sleeves until about March. Not totally. You're right. I'm not random. So, true random number generators are actually really hard to find. And one of the earliest random number generators used to be pi. They knew pi to a whole bunch, millions and millions of decimal places, and they decided those numbers are random, or at least random enough. So they tell the computer, I want a two-digit number, and the computer would just go and randomly pick two digits out of pi in like two in a row. But even that's not totally random because some number combinations don't even show up. So truly random is hard to do. We do have some number generators that are random these days, but no, not at all. Oh yeah. Oh yeah. Not random. So, somebody says pick a random number. Okay, pick a random number. See, was that truly random? No. How many numbers out there are actually whole numbers? Almost none of them, right? And you chose a whole number. That was not random. Yeah, 7.37654. That's more random than 7. Okay. All right, number 6. We talked about control groups, and sometimes it makes sense to talk to a lot of people and then categorize those people by age or gender or weight or height or whatever you want, and then compare, similar heights or similar ages. For instance, smoking, um, it doesn't make sense to compare the blood pressure of women in their 80s who smoke to women in their 20s who smoke. No, it just doesn't make any sense because blood pressure goes up with age. So sometimes we take a controlled experiment, we break it into categories, and then we look at categories. Um, okay, 7 we don't really need to worry about. All right, descriptive statistics. So we're on page 50. Where are we? 56. So a histogram, you guys know it as a bar graph. And this book does something a little strange that I'd never seen before. And it did the percentages, and it had class intervals that were different lengths. And that doesn't turn out to be a huge deal on the tests, but you guys understand that if this group contains 25% and this group contains 25%, one of them is a lot taller. Which one? The one on the right has to be taller because that area and this area have to be equal. Now, we can avoid that problem by doing something that's really simple. Make all the intervals the same, and that's what I recommend you do. If all of your intervals are the same width, then you can just graph the height as a number. And that's kind of how you avoid it, yeah. I don't think so, but I'll double check. I don't think this is a problem, but I'll look at it. So that's the density scale. And number 5, you guys know what variable is. Number 4, what is a qualitative variable? It's a quality described in words. Give me an example of a qualitative variable. Hair color, taste, the name of your boyfriend or girlfriend. That's so for some of you that's a bad quality, right? That's like a negative quantitative variable. Okay, what is a quantitative variable? It's a number, age, height, weight, score on a test, time. Yep, time can be. Quantity means number, so quantitative is a number. Um, Quantitative variables can be split into discrete or continuous. What does continuous mean? There are no gaps. Give me a quantitative variable that is continuous. What? Well, that's not a variable. That's a constant. It doesn't change. What's something we can measure that's continuous? Weight is truly continuous, right? But do we treat weight as a discrete entity? No. We always list weight to the nearest pound or tenth of a pound. I weigh 193.2 pounds or something like that. So weight is truly continuous, but we kind of treat it as though it's discrete. What else is continuous? Age is continuous. Yep. We kind of treat that as discrete. We round to the nearest number, or actually we round down for some reason. Isn't that weird? I am 35, and in 2 weeks I will turn 36. So I'm almost 36, but I'm still 35 until that day happens. Okay, what is a discrete variable? The number of watermelons in my fridge, right? I guess you could have half a watermelon. So we talked about how much and how many, and less and fewer. So anything that you would say much with, like I have too much sugar, is continuous. Okay, I I have too much gasoline in my gas tank. It's not countable. You can't count gasoline. It's continuous. But you can count gallons of gasoline. I have too many gallons of gasoline. Does that make sense? So there are too many people in this class, and some of you I don't like, right? You guys are countable. Even the short ones are a whole person. And Megan, you don't get extra credit for being tall. Okay? And then we're not very good at less and fewer. You go to Walmart and it says 20 items or less. Less is not countable and fewer is. So it should say 20 items or fewer. So I scored fewer points on the test than you did. And you guys just say less for everything, which is wrong. Okay? Um, I have uh, I have fewer bed bugs at my house than you do. Bed bugs are countable. Okay? There is less gasoline in my gas tank than in yours because gasoline is continuous. Well, hypothetical. All right, and then number 5, cross tabulation. That's where you categorize things and you compare similar categories. And sometimes that eliminates confounding variables. All right, average and standard deviation. So this is page 76. A typical list of numbers can be summarized by its average and standard deviation. What is an average? It's the sum of everything divided by the number. What does the average tell us? If I randomly, here, I'm being terrible, hand everybody a pocket full of M&Ms, what does the average tell me? It essentially means if I distributed all of the M&Ms evenly, the average is how many everybody would have, right? Some people got a big handful, some people got a small handful, and an average would be if I redistributed everything evenly, that's how many everything would have. But chances are not many or nobody is actually at the exact average. Okay, and because of that, we need to know how far apart things are, and we use something called the standard deviation. What does the standard deviation tell me? It's the average distance from the average. So let's say the average was 50 M&Ms with an SD of 10. That means if we were to count how far everybody was away from 50 and then redistribute those evenly, then everybody would be 10 off. But the SD is not the true average from the average. It's actually a little higher than that. It's a little bit bigger than the true average. Um, well, there are a couple reasons. One is the inflection reason that I've told you a whole bunch of times. And the other is, in statistics, nothing is perfect. And so we would rather err on the side of safety. So we have our choice between the SD is 9.5 or 10. 10 is safer. And that's one of the reasons. And when you get further into it, we actually can build equations that work. And it turns out that the root mean squared average is perfect. Now, why that's the case is a little bit of a mystery, but it actually works out perfectly. And then sometimes the SD is not big enough and we bump it up a little bit more, but you won't see that for a while. Okay. So when we talk about a histogram, and instead of drawing a histogram, I'm just going to draw a curve. Okay. This number right here is different from this number right here. This one would be called the median, and this one would be called the average. Now that median is the middle number, so we're not going to use that definition. What does the median mean on a graph? Half of the people are on the left and half are on the right, and it's in terms of area. So we can look at it as area or people, and maybe I didn't draw that very well. Watch this. I learned this new trick. Ooh. Okay. So half the area is to the left of this red line, and half the area is to the right. Now, what about the average? What does that tell me? It's the middle of the weight. Okay, and why are the median and the average in different places? Because that tail on the right contains really heavy people. And we might not be talking about weight, we might be talking about income, but the people on the right, there aren't many over there, but their values are so much higher than the others that they pull the average toward them. Okay, so let's say I take one person, this person right here, okay, and I move that person, I give them a huge raise, now they're making $10 million. What does that do to the median? Nothing, because that person was already on the right, right? I started right here, and I move a little tiny bit of my area over here. Is there still 50% of the area on the right? Yes. But what's going to happen to my average? It's going to slide this way and be less representative of the actual one. Yes, that would make the SD go up. Okay, so what if I take this person and I move him there? The median will move half a person to the left, right? If we move two people, it would move one person. And then the average is going to slide just, they're both going to slide just a little bit that way. Okay, now if I take this person and I move him over here, what happens to the median? Nothing. The area is still the same, but my average is now going to bump to the left a little bit. Okay, and we're going to talk about outliers. I mean, if all of my people ended there and I have one person way up here, maybe I don't want to include them, or maybe I do. That's called an outlier, and we'll talk about outliers later. Okay, the root mean squared, you just need to know that it exists. You don't need to know how to calculate it. You will never calculate standard deviation by hand again. But just remember that the root mean squared is slightly larger than the actual average. Okay, number 7, SD measures distance from the average. And then number 8, we have our poster up on the wall. One SD to the right and one SD to the left captures 68% of everybody. Now, we've been doing that in our assignments. How often are we exactly 68%? We're not. We're usually off by a little bit, and that's called statistics. You're just never totally there. So we say about 68%. And sometimes we're high and sometimes we're low. Okay, and then if we go out 2 SDs, we're at 95%. And if we go out 3, we're at 99.7. And there really aren't very many people outside of 3. And this only works if the curve is normal. Okay, if it's a bell curve, right? Lots of people in the middle and few people toward the edges. If you have any other shape, then this 68, 95, 99.7 rule doesn't apply. The 68% rule works most of the time, but outside that, you run into problems. Okay. Number 9, if a study draws conclusions about the effects of age, find out whether the data are cross-sectional or longitudinal. Okay, what does a cross-sectional study mean? It's like the slice of pepperoni. You take the pepperoni, you cut it, and you look at that one slice, right, the face of it. So a cross-sectional is a snapshot in time. It's a picture that occurred in one moment. What does longitudinal mean? You follow the same people over time. Okay? You can do a bunch of cross-sectionals, but they might not be the same people. A longitudinal means I follow Aubrey for 10 years. Sorry, Aubrey's. Okay, I've been measuring for the last 10 years which one's been nicer. And that is longitudinal. You follow the same people over time. Okay. So if I measured height in this class in 1050 every year, I would have a series of cross-sectional data, right? But if I followed you from year to year, that would be longitudinal. So longitudinal requires you follow the same people. And cross-sectional is just a picture in time. Okay. Now for chapter 5. Oh, I'm in 6. What page? 96? Thank you. Okay. The normal curve is symmetric about 0, and the total area is under it is 100%. You know that? Standard units say how many SDs a value is positive above or negative below the average. We've spent quite a bit of time on that, and you have to understand this part in chapter 5 because it never goes away. We will use it up until the last day. Okay, 3, many histograms have roughly the same shape as the normal curve. And if your histogram looks sort of normal, then we use the normal curve. Okay? If a list of numbers follows the normal curve, the percentage of entries fallen in a given interval can be estimated by converting to the standard units. Okay, so let's do an example of that. Here is some totally made up data. We are looking at the IQ of people in this class. So the average IQ in this class is 115. Okay, with an SD of, let's say 9. All right. So if my IQ is 110, what is my percentile? So I draw the normal curve centered on 115, and I want 110, which is over here. So 110. How do I find a z-score? Subtract which way? 110 minus 115 divided by 9. So 110 minus 115. And make sure you push enter. What does negative 5 mean? I am 5 IQ points below average. Okay, and I divide that by 9. And this gives me my z-score in standard units. What does negative 0.55 mean? I'm 55% of an SD below average. Okay, so how do I find my percentile? Shade norm. So let me clear out my graph first. And zoom, I'm going to go to zoom recall. And then shade norm. Camry, it works for you now. You know what you're doing. And I'm going to shade from negative infinity to negative 0.555. Comma 0, comma 1. And I should get a left tail here with a percentage that is 29%. What does 29% mean? I'm in the 29th percentile, meaning my IQ is higher than 29 out of 100 people in this class. Okay. Now this class is less than 100, so and actually a data set this big isn't. We like bigger data sets. 25 kids is really. We prefer something much bigger. Okay. So what if I change it? And instead of 110, I want 129. So I draw the same curve, 115, and over here somewhere is 129. And I do 129 minus 115, which is 14. Divide that by 9. So 14 divided by 9 gives me 1.55. So clear out my draws. And I'm going to shade norm from from negative infinity, so negative 5, to 1.55 with my 0 and 1. And I get 9, is that a 9? 94%. Which means my IQ is higher than 94% of the people. Okay. What if I had this? What if I wanted to know how many people in the class have an IQ that is larger than 113? So I draw my curve. I put 115 in the middle. 113 is just slightly to the left. So 113 minus 115 is -2. Divide that by 9. And I want to shade from -2/9 to 5 or 100 or infinity, whatever you want to put. Okay. Shade norm from, and the nice thing is you can actually just type in fractions right there, and it won't care. Oh, did I not? I did that wrong. Yeah, I wanted to go from -2/9 to 5. Sorry, guys. Yeah, I could have just subtracted 100 from it. You're right. And I get 58.7, meaning 58% of the people in this class have an IQ higher than 113. Okay? Does that make sense? All right, the ones that tend to confuse people are the ones where you go backwards. So same situation. I want to know if you are the 38th percentile, what is your IQ? How do we do that? We draw the graph. Where does the 38th percentile land? To the left of the average. So this area is 38. So the other side is also 38, and 38 plus 38 is 76. So 100 minus 76 is 24, and 24 must be in the center. So that is the area. And remember, when you go backwards, don't look at the left column on your yellow paper. Look on the right column. So I go to 24%, which is, what would you say, 0.31? Some 0.3, 0.31, it's right around there. So my z is equal to negative, good, negative 0.31. Okay. What does negative 0.31 tell me? That's how many SDs below the average this person scored. But I don't want to know how many SDs. I want to know IQ points. How do I convert Z back into IQ points? Times it by the SD. So I multiply that by 9. 9 times negative 0.31. Now what does negative 2.79 tell me? That's how many IQ points this person is below average. So we're going to add 115, and we get 112.21. And again, those formulas are up on the wall under that 95, 80, 68 curve. To find Z, value minus average divided by the SD. To find a value, you take your Z score and you times it by the SD, and then you add back the average. You would always add the average. Yeah, because we want to make sure that our Z score always has the right sign. So your Z score needs to be negative if it's on the left and positive on the right. Okay, same story. Who is in the 81st percentile. Draw my curve. Where is the 81st percentile? It's on the right. So if this is 81%, then this is 19%. So I need to cut off 19% over here. 19 and 19 is 38, which means that the center must be 62%. Now, does everybody understand how that works? Okay, so I look up 0.62 on my z-score chart, and I get 0.88. Is it positive or negative? Positive, because we want this one. 0.88. What does 0.88 mean? That's 0.88 SDs larger than average. But I don't want SDs, I want IQ points. So I multiply that by 9. What does 7.92 tell me? That's how many IQ points this person is larger than average. So we add on the 115, and we get 122.92. That person scored in the 81st percentile. Okay? And that's chapter 5. I mean, that's pretty much it. Any questions? Yes. Okay, let me take a look at that. All right. So let's look at how you build a histogram. And because the book does this way, we're going to make some that have class intervals that are different sizes. So what would be good? So let's talk about income. Okay. So income. So we'll go from, this will be in thousands of dollars per year. So from 0 to 10,000, there are 14% of the people. Okay. And then from 10,000 to 15,000, there are 8% of the people. And 15 to 20, there are 12%. And then 20 to 30, there are 20%. And then 30 to 50, we have 20%. How much is that? 2, 4, 6, 74. 50 to 60, we have 16%. So what am I up to? 90. And then from 60 to 100, we have 10%. Okay? So how do we draw this histogram? Well, we need to figure out how wide each interval is. So this is percent, and this is width. How wide is the first interval? 10,000. And then 5, 5, 10, 20, 10, and 40. Okay? So I'm going to start drawing my histogram. So let me go all the way up to 100. 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. So my first interval is this big. Okay? And my second interval, if I go back up, is 5. So I've got an interval that's this big, and then I have another interval that's that big. Okay? And my next interval is 10. So this big. And then 20. So 10, 20, and then, oops, 10, and then 1, 2, 3, and then 40. Okay? Does everybody understand the widths? Now I need to calculate the heights. Well, this row here contains 14% of the people, and the width is 10. So how tall does that box need to be? It would be 14 divided by 10, which is 1.4%. Does that make sense? Okay. If this is 8% and the width is 5, what is 8 divided by 5? 1.6? 1.6%. Okay. Now what about this one? 2.4. 2/5 is 4, so 2.4%. Okay. What about this one? 2%. And the next one? 1%. And the next one? 1.6%. And 10 divided by 4 is 0.25. So why did I put all these first before I graphed them? So I would know the height. The tallest one is 2.4. Okay. So down here, I draw my y-axis, and I'm going to say 1. That's probably a little too big. So 1, 2, 3. And then I can do the halves. So my first box has a width of 10. And if I go up, the height is 1.4. So 1/2, 1, 1.4 is right here. Good. If the intervals were the same length, then the heights would just be the percentages, or whatever numbers in that column, which makes a lot more sense, right? Just make all of your boxes the same height. But if you are offered one where the class intervals are not the same height, then you can't recategorize it. Okay. All right, so that is my first box. My next one has a width of 5 and a height of 1.6. So 1.6 is about right here. Now, which one contains more area, the red or the blue? The red, but the blue is taller, but it's narrower. And you can actually see that up here. The first block has 14%, and the second block has 8%. Okay, and the width times the height is the area. Okay. All right, the next one, I have a width of 5 and a height of 2.4. So I'm going to go up to 2.4, which is right there. Now, which one has more area, the black or the red? Well, let's look up here. 14% compared to 12%. Okay. All right, and then the next red one is going to be 20%, width of 10. So we go up to 2. So we go up here to 2. And that has more area than the red one because it has the same width, but it's taller. Okay. And then the next one, we go up to 1%, has a width of 20, and we go up to 1%. Oh, I used the wrong color, but whatever. Okay. And then the next one has a width of 10 and a height of 1.6. So 1.6. And then the last one has a height of 1/4, and it's really wide. Does that make sense? So you need to be able to look at the class intervals and create widths, and then use those widths to create heights, and then you graph the class intervals and the heights. And do this entire table before you label the y-axis, because you need to know which one is the biggest. And you can't just look over here and say, oh, 20%, that's the biggest. Because that class interval is wider than the others, so it ends up being pretty small, pretty short. Okay. Do you guys think you can handle that, or do you need to see more histograms? Think you're good? All right, let me take a look. You can, but I don't think we're not going to ask you a question like that. And nobody draws histograms by hand anymore. They just get the data and they tell the computer, draw me a histogram, and then the computer does it for you. You know, you can choose your class intervals, or you can do it however you want, but I don't imagine you're ever going to have to draw these by hand again. But on the test, you need to know how to draw a histogram. Okay. So I just made this up about income, but what does the income graph really look like? The income graph is right-tailed. And it doesn't really matter where you go, the income graph is going to be right-tailed. Right? The bulk of the people, right, this chunk of people, the middle class, are in the middle. And then you have low income, the poor people, and then high income. So income is not normally distributed. So on an income graph, which is further to the right, the average or the median? The average is further to the right. Okay, any other questions? All right. No, you can't.